This video is going to show a more complicated example of Monte Carlo error propagation, specifically applied to the data from Muth and Wallace 2021. And we're going to be looking at their XANES sulfur 6+ measurements and how they compare to different models for predicting sulfur 6+. So you're going to go and read the docs. As normal, you should watch the first Monte Carlo video first. Click NB Viewer, download the notebook, open it up, and you'll also want to download the Excel spreadsheet that goes with it. So I'm just going to show you what that looks like. So this is basically their supplement, and I've merged different sheets from the supplement based on the melt inclusion name. If you're interested in how I did that, there's another Python notebook for that on GitHub. You can basically see what we have is we have the silica content of a liquid, and the 1 sigma error, and these were all from their supplement. So this is basically the data that we're going to be using. You can see there's also the water content error, so on and so forth, along with lots and lots of other columns. So we're going to import our Python stuff as normal, and then we are going to load this data, and we're going to use the SS import data function. And what this does is it's going to take all those column headings that you want, the SiO2 liquid, the titanium liquid, and it's going to put them to the front. And because there's tons and tons and tons of other columns in this spreadsheet, what I'm going to do is here, I am taking only sort of the first 12 columns. So that's all the columns that I need for these calculations. So you can see that here. So we've got all of the oxides, the water content, the iron 3+, and the sample ID. And we're going to call this data frame out trim. So we've got all of the columns we might want stored in data frame out, but we've trimmed it just for simplicity. And then I'm also just going to rename, in the spreadsheet, this was called melt inclusion name. I'm just going to rename this sample ID liquid, just for simplicity, and then have a look at that. I am then going to load the same spreadsheet, but instead of using the import data function, I'm using the import data noise function. And what this does is it moves all the columns with like SiO2 liquid error to the front. So this means, again, I can just trim the first 12 columns, and I get a kind of much smaller data frame that's nice to work with. Now, if you read Hugh O'Neill's paper with XANES from 2022, they actually correct these XANES measurements using the Berry correction, and this is because of offset in XANES calibration and fitting routines. So we're just going to do that here. So we've already got the iron 3+ iron total ratio that Muth and Wallace prefer, and then we're also just going to add another column, which is the 3+ relative to Berry, and we're going to just make sure that the error for that is the same as the error for the other one. Okay, so just adding another column. So you can see that if you use the Berry correction, you get about 0.11, so 11% iron 3+ in the first, and before that correction, it's about 15%. So this is a reasonably big difference. Okay, so what we need for a lot of the calculations is a temperature. So here we are giving Thermobar, which is the thermobrometry package, and you'll have to import this if you haven't already. You will use the calculate liquid only temperature, and you're going to give the liquid compositions and then equation 22 of Paterka 2008. At a pressure of 3 kilobars, that's what they use in their paper, and at the water contents. Okay. So let's just perform calculations for the measured melt inclusions first. So we're giving it the data frame. This is our trimmed data frame. We're giving it the temperatures that we calculated, and we're giving it initially the reported iron 3+. So this is what they published. So you can see you have about 21% sulfur 6+ in the first sample, 86% in the second, and so on. We can do the same calculation, but this time we're using Fe3+ after the Berry correction. And you can see this drastically changes the amount of sulfur 6+. So lower iron 3, lower sulfur 6. We can just plot these on a one-to-one line. So here we are just plotting on the x-axis what they actually measured, and on the y-axis what we've calculated. So actually you can see that using their reported iron 3+ is a lot better match than using the Berry correction. So that's kind of interesting. And again, we can just run the statistics here, and we can see they're very similar R squared, but the root mean squared error using the reported iron 3+ is a lot better than using the Berry correction. Okay, let's do some Monte Carlo simulations, which is why you're watching this video. So for each melt inclusion, we're going to make 5,000 duplicates. We are going to add in an error on the temperature, because although there were errors in the input data frame, in the input spreadsheet, there wasn't a temperature and a temperature error. So we're setting the temperature in the liquid to this temp 3 that we calculated up here. So here, and then we are also saying that there's a 50 Kelvin 1 sigma uncertainty on that. So now we've appended that onto our data frame out and our data frame error. We then are going to use the function add noise to data frames, and this is discussed in more detail in a previous video, which I encourage you to watch. So we're saying these are absolute errors, they're normally distributed, and we want 5,000 duplicates. Okay, so that's just going to plow through. And there's quite a lot of samples and you're making 5,000 duplicates, so that's why this is just going to take a second. So you can just see that if we look at the length of this, this is, you know, it's a lot of zeros, but 150,000 rows. Okay, so now let's calculate sulfur 6 plus for all of these rows. There's 5,000 duplicates per sample. So we're going to input the data frame that we've made up here, data frame noisy absolute. We're going to input the Fe3 plus ratio, the measured kind of conversion, and also the berry one down here. So we're going to make two different Monte Carlo simulations. And again, giving it the temperature which we've just made here. And that's obviously going to take a second because that's a lot of calculations. And now we're going to use this average noise sample series. So again, watch the previous video. But basically, we want to take this data frame and we want to take the sulfur 6 plus sulfur total ratio, and we're doing it for the reported one first, and we're averaging based on the sample ID, and we can do the same for the berry thing. So what you can see is for each sample, it tells us how many rows it averaged, what the mean sulfur 6 plus, the median, the standard deviation, the min, and the max. So you can compare those. Let's do the same for Nash. So another way that you can do sort of these Monte Carlo simulations is instead of duplicating two data frames, you can just take one data frame, make as many rows as you want, and then append on certain columns that have uncertainty added. That's what we're going to do here. We're going to duplicate the first data frame. And we are now going to use the add noise series function to basically take the temperature and add the 50 Kelvin of uncertainty, okay? And we're going to do the same for iron 3. And this is because Nash only requires temperature in iron 3+. So it means we have a lot more flexibility to do these things, okay? So now we've got a column of temperatures, which has, 150,000 individual things, and we're appending that onto this duplicated data frame here. And we're going to do the same with the iron 3. So you can look at this, and now what you have, this is just another way of doing this. All the major elements are exactly the same, but you now have here temperature and here iron 3+, which has had noise added to it. So we're going to put these uncertainties into Nash, and here we're just using the measured iron content, not the berry corrected, but you could change this to use berry, not a problem. And then again, we're going to average over all those rows by the sample ID. Okay, so for the Jugo sulfur 6 plus parameterization, we only have iron total. So we want to calculate delta QFM, and specifically Jugo requires delta QFM relative to the frost position of the QFM buffer. So here we're using thermobar, so again, you'll have to import that package. Basically, you're converting iron partition to FO2, so you can give it your liquid compositions, and here we're not necessarily propagating the uncertainty in these. So this is not looking at the variation because of major element content. This is actually at the moment just propagating temperature and iron 3+ uncertainty. But similarly, you could swap this out for the first one if you also wanted to look at the impact of the major elements on that. So we can run that here, and then we're going to calculate Jugo. And again, this has lots and lots and lots of rows, and we are going to average them here. So what you can see is that you can see the standard deviation here is about 0.03 for this one, 0.22, etc. So what we can say is you can say, well, the major elements are probably quite important, and that would be perfectly reasonable. So let's go and grab our duplicated data frame here. So the one we made up above. So if instead we're going to give it the noisy major elements, let's see how that varies. So I'm just going to navigate back to here. Okay, so if we remember that this one here, we're looking at the Uncertainty, so we're going to look at this one, 0.22. Okay, let's see how much that number changes. So here, I'm going to give it that instead and propagate that through. So you can see actually this hasn't made an enormous amount of difference. So maybe a little bit bigger, we can, you could take a screenshot of this, or you could make two separate variables to look into this more. But actually it doesn't seem like that's had a major impact on the calculation. So this is the kind of things you can play around with. One other thing that you might want to do is convert the sulfur type. So basically, if we look at how sulfur is stored in their data frame, we can see that they've stored it as weight %. So we're going to want to convert it to ppm. So you can just use this function and it gives you the ppm and the weight % of all the different ways you might want to express sulfur. And then we're going to plot for one sample what the distribution of input parameters look like. So this is what they look like. And then what we're going to do is we're going to plot the measured sulfur 6+ ratio from XANES. We're going to plot the mean of the average, and this is for the O'Neill method. And then we're going to plot the Y error bar as the standard deviation. So we're going to do that for O'Neill, do that for Nash, and we're going to do that for Jugo. And you can see now you have the measured sulfur 6+ ratio, and through Monte Carlo methods, you have an error for the calculated sulfur 6+ for each one of these. So this is pretty useful in terms of actually knowing what is the uncertainty on these methods. We could show the same using Berry, and you can see similar size error bars, but it's doing a lot worse job for this data, which is interesting. And again, we've calculated these stats before, so we can just delete these now. You can also do Monte Carlo simulations like this for calculating the SCSS for these samples, the SCAS and the S total. I'm not going to talk through those, but basically it's the same structure and you can follow through the rest of this workbook if you're interested.